Right, FRQ 2 for AP Physics C E&M in the sample question. This is for the sample exam, sorry. This is relatively straightforward compared to question 1. But let's see, it's a good question, conceptual one. So there is a solenoid, there are so many turns, and this is X, Y, Z axis marked over here. The length of the solenoid is much larger than the radius of the solenoid loops. Now we are given a cross-sectional view of the solenoid where this is the current and counter in a clockwise sense. There are three squares, 1, 2, and 3, placed at the center, off the center, and then outside. And we have to figure out that what is the direction of the magnetic field at these three little squares out of these options. And if 0 is the answer, then we just have to indicate 0. So this is pretty straightforward, because we are going to find out the direction using the right hand curl rule, where we take our right hand and curl our right hand, the fingers of the right hand towards the current in this case. So obviously the hand will point, we have to turn our hand, right? And if we do that, the thumb will point into the page in this case. Into the page means it's the negative z-axis, and the negative z-axis is represented by a cross. Now, it doesn't really matter whether the square is at the center or a little off, because inside the solenoid, the magnetic field is uniform and constant. So it is not going to change. So it should be a cross here and it should be a cross here. And we should also know that outside the solenoid, the magnetic field is just 0. So this is a concept that we should be aware of. All right, the next they're talking about that now the solenoid has a current of I, which is varying as a function of time right here, and inside that we put a loop of radius R naught, and the radius of the solenoid is 3 R naught, and they are asking us to derive an expression for the absolute value of induced EMF in the smaller loop for time t greater than equal to 0, and our answer should be in these terms. It has n naught turns per unit, by the way, the solenoid. So we know that if you want to find the EMF, then EMF as per the Lenz's law, Faraday's and Lenz's law. I'm just interested in the magnitude, so I will put this absolute value of d phi over dt, where phi is the flux. We know that the flux is given by B dot A, so it's B dot A right here. And in this case, the magnetic field, as we have already figured out, is pointing into the page, and the area vector is also pointing into the page. So, the dot product will just be cos 0, because the angle between the magnetic field and the area vector is 0, and cos 0 is 1. So the dot product is can be taken off, it's just BA. All right. Now, what is B? B is the magnetic field due to the solenoid, that has a formula of mu naught times I of the solenoid times number of turns per unit length, which is n naught. And area is the area of the small loop, which is pi r naught square. And we have to take the derivative of this entire thing. I'm just going to drop absolute value because I'm not putting any negative sign anywhere as of now, or otherwise you can just put it. Maybe later on it will come. Now, mu naught, n naught, pi, r naught squared, these all are constants. So that is going to come out because that has no job inside the derivative. So this is how it's going to look like. And we have to take the derivative of I, which is as a function of time. It's I naught times 1 minus bt square. All right. And all we have to do is differentiate this. So if we differentiate this, then I naught is a constant, just remains as it is. And the derivative of 1 minus bt square is 0 minus 2bt with an absolute value over here. And this is mu naught, n naught, pi, r naught square. And the negative sign, the absolute value is going to eat the negative sign. And we are finally be left with mu naught, n naught, pi, r naught square, I naught times 2bt in terms of time. So this is the EMF, induced EMF in the small loop. Over here on this axis, we have to sketch the magnetic flux through the small conducting loop as a function of time. And we also have to indicate the horizontal, the x-intercept, actually the horizontal axis where the flux is 0. So let's rewrite the expression. Flux was BA. the magnetic field is mu naught times I times n naught and pi r naught square, and I is given by some mu naught n naught pi r naught square, and I will be I naught times 1 minus bt square, right? Right, this is just a big constant, right? So I can just replace it for the moment with some constant k just to analyze, and this is 1 minus bt square. Now, in order to find the x-intercept, I'm going to set this entire thing to 0. So k times 1 minus bt square will be 0, which means that 1 minus bt square will be 0, which means that 1 is equal to bt square, which means that 1 over b is t square, which means that if I take square root both the sides, then 1 over square root of b is t. I know I should put plus and minus, but time cannot be negative, right? So we just have to graph anyway for the positive sense. So this is the x-intercept, which is 1 over root b. And how will the shape look like? Don't you think this is a parabola? I mean, this is y and this is x after all. So this is a parabola, and clearly this is opening towards minus y-axis, right? Because there's a negative sign right here. What is the vertex, by the way, of this? The vertex is going to, I mean, I can decorate this. So if the flux is going to be, if k is taken inside, it will look like negative k b t square plus k. So as we can see that t doesn't have anything inside, so the h is just 0, and the y coordinate of the vertex is just this value, which is k. K is obviously our assumed variable, which is this entire thing. So this is going to be the vertex 0 comma k, and it's going to open downwards and have an x-intercept of 1 over root b. If we want to indicate this, we can also say that this is mu naught n naught pi r naught square I naught as well, if we are interested to mention that. That's totally fine. So so that's how it looks like. Finally, indicate the factor by which the vertical intercept of the graph, it means the y-intercept, you drew in part C would change, if at all, if the loop inside the solenoid has a radius of 2r0. Pretty straightforward. We already have k right over here, correct, which is actually the y-intercept. So if this, how will this change, which we have marked as k, if the radius r0 is now 2r0? So clearly, all the other things will not change. But the moment I change this with 2r0, remember that this 2 is also supposed to be squared. So that 2 squared, which is 4, comes outside, and all the other things remain as it is, which clearly means that it will become 4 times of the initial value. So this is the k new, which is the y-intercept, and this is the k old. So k new will actually become 4 times of the y-intercept will become 4 times of the initial value.